Okay, guys. Uh, let's get started with our new topic, which is deflections. Okay, so the main part of this remaining course will be focused upon deflections of determinate structures. Mainly, we will be concerned with the deflections of determinate structures. But I will introduce you to different methods which are used for working out deflections. So far, what we have done is carrying out structure analysis. Okay, so you do you work out the reactions based on the applied load, and then you draw shear force bending moment diagrams. Now, after that, once you know the structure analysis, then you come up to find out deflections. Okay, so it's a step forward to whatever we have done so far. Deflection is normally concerned with the serviceability of structures. By serviceability, we mean, in general, deflections don't cause your structure to collapse. What does deflection mean? Deflection means that visibly you can visualize a structure which is bent. Okay, so in other words, we have got this structure. May I please ask you not to talk? Okay, this is the last time I'm asking you, because then I don't want to use some harsh words, really. Look, it's Ramzan and I don't want to use that. So please, once, twice and third time, I don't want to say it again, okay? So I'll appreciate if you don't talk. Yes, so what we mean is that if we have a structure, okay, once you cast a structure, for example, we are talking about reinforced concrete structures, you cast it somewhere. Initially, when you look at it, when an engineer look at it from a distance, so he or she has to make sure that it is straight. Okay, it is not bent like this. Visually, if it is bent, then obviously something is going wrong. Until and unless you have designed it in such a way for different purpose, like for architectural purpose. The architects want a sort of a structure which has got which is bent, which is deflected. Okay, because just for visual appearance, so that's different. But in general, when you cast a structure, you want it to be straight, visual. Okay. If the structure is not straight, then what happens? So once you cast it, then you apply the load on it. How do you apply the load? By casting your additional structure. So the additional structure would have its dead load contributing to the main structure, like under consideration. Like for example, if it's a beam, it will slightly deflect. Then once your whole structure is built, then you subject it to the loading. Okay, like loading of live loads, dead loads. By live loads, I mean like people walking on it. Yeah. Then you have superimposed dead load. Superimposed dead load is your like desks, equipments, or that sort of thing which you place on it once your structure is built. So those items will contribute. Will apply additional load on your structure, and your structure will tend to bend. Now, you have to make sure that visually, under application of all the loads, your structure don't bend to an extent that it gives, it disturbs the people looking at it, or the people who are utilizing it. Okay, you being sitting in this class, okay, you don't want that there should be a beam hanging like swings, okay, over here, because obviously if you see just a structure which is bent so much, yeah, that gives sort of dissatisfaction. Okay, so that's something which you have to avoid. So it's not necessarily, it might be designed in such a way that it can take additional load. The structure might be designed in such a way that it can absorb additional load. However, visually it is not passing your visual test. So that is also termed as failure. Okay, because if the people can't use it, for example, imagine you want to go and you want to buy a house, okay, and you see that the beams in a main hall, main lounge, okay, a big hall, they are bent so much, they are deflected so much that it is hardly few inches above your head. So obviously that will put you off from buying that structure. You would realize, you would think that, you know, that structure might collapse in some time future. Although the engineer might argue that no, it's not gonna happen. Why? Because the beams are designed, it can take it has got enough ductility, it can take all the load, it is very elastic, blah blah blah, but you are not going to go for that. Okay, so one thing is that your structure is not able to take the load. Okay, you apply the load and it crushes. You would be doing you would have done cube test, cylinder test, isn't it? Yeah. When you keep on applying the load, visually you can see that that your concrete, it starts falling off. You are not able to apply the load, it becomes soft, it's not able to take the load. So that is a visual collapse. Okay, like, you know, in the case of beam, you apply so much load, or in other words, you subject it to so much seismic load that it crushes. Okay, it collapses, it falls down. So that is a clear failure. Okay, that's a structure failure. This is deflection is among the serviceability failure. In other words, the people who are using it, who are for them, it becomes a failure. Okay, design wise, it might be able to take the load, but for the people using that structure, might not be satisfactory. So, in other words, so deflection is one type of serviceability. The other aspects of serviceability can be cracks. You see visual cracks appearing. Now again, you would have done, there are hairline cracks. There are cracks which appear under the below steel. Okay. In other words, I mean, like in reinforced concrete, I think so. You are not yet introduced to reinforced concrete, but there are small cracks which are not structural. But if they become too big, obviously, then it becomes disturbing for people who are using that structure, isn't it? Okay, structurally, maybe it might be okay. So that is another serviceability aspect. Another thing is you have got floor, and the floor is so thin, yeah, that people walking on it, it starts vibrating. That is also a serviceability failure. So people who are using, who are servicing that structure, who are utilizing that structure, for them, if it caused any sort of dissatisfaction, if it caused any sort of disturbance, okay, then that is also classed as failure. So deflection is the most important thing among all those serviceability aspects. Okay, so deflection, what happens? As I said, you have got a straight structure, and for some reason it starts taking load and it bends like this. Okay, it deflects. In other words, the main center line which was straight, every structure deflects. Okay, so when you apply load on any sort of structure, it will deflect. But that deflection has got limitation. The code of practices, they impose certain limitation on that deflection. If it goes beyond that deflection, then visually it becomes apparent. You don't want that deflection to be visually apparent. Do you understand my point? So what I am saying is that deflection is very important, and for that you must know the mean to work out the deflection. Okay, so therefore this topic is introduced to you guys to make you understand how to work out deflection. Now to design for deflection, that will be for the other module, okay, which might be steel structures, reinforced concrete structures. So that is different. We are not going into the design aspect. We are just limiting ourselves to to finding deflections, okay, using mechanics which you have already done in your MOS 1 and engineering mechanics. Okay, so using those tools, we will derive our deflection equations. We will derive different methods, and based on those methods, we will work out deflections. Okay, so now initially I'll introduce you to the mechanics. So the same sort of mechanics. First of all, to flexure formula, the most important, or it's also called engineer's beam equation, stress is equal to My or I. I'll just refresh your memory. You have done it in your MOS 1, how to derive that, and then taking from there how to work out your deflection. Remember, deflection is a geometrical aspect. It is related to the geometry of the structure, isn't it? So therefore, you must be familiar, or you must get yourself familiar with another geometrical aspect which is very commonly used in deflection, and that is called curvatures and radius of curvatures. Okay, so that is something which I would introduce you to, or if you have already done, I mean, like, I'll just build up on that concept. So first of all, just a very quick refresher of engineer's beam theory. Okay, engineer's beam theory. Any questions so far? Any question? Okay, now what is engineer's beam theory or the flexure equation? Yeah, the flexure equation, what we are trying to do is finding out how much a particular layer will be stretched or will be compressed. That is the whole aim. For example, I have got a rod. Yeah, I've got a rod. I apply a load, a tension load on it. It will elongate. It will elongate, and that elongation we must we as a structure mechanicians, as a structure engineer, we must know how much is that elongation or how much is that deformation. Okay, so the engineer's beam theory, that is particularly used to find out different layers which are either elongating or either compressing. Okay, but everything is happening at the same time. In other words, we have, for example, a structure. Imagine it's a beam which is subjected to some sort of loading. Yes, and this loading, under this loading, the beam will bend. So visually, there is no such thing as elongation or compression. Okay, so you have to go deeper into bending and work out your elongations and compressions. Okay, so how do we do that? We assume that the beam, this beam which we are using in our thought experiment, that is made up of lots of slices. Okay, so we assume that it is made up of infinite slices. Okay, and once you apply a load, for example, we have got a load applied on this structure. It can be any generic load. This will bend. Okay, the beam will bend, and what will happen? These somehow. So bending means that some of these layers, so you have actually sliced it. Okay, you have sliced these beams into infinite layers. Some of these layers will be in tension and some of them will be in compression. Okay, and we know that stress is equal to P by A, and okay, so, and also we know that what is the displacement of a structure which is subjected to tension or a compression? Yeah, but what is, how do we work out the displacement of that? Yeah, so that displacement is PL over AE. That is something which we have, or in other words, delta is equal to stress L over E. That is the displacement. Okay, so for that, or in other words, this is actually derived from stress is equal to E times strain. Why? Because this is change in length by original length. So actually everything comes out of your simple Hooke's law. Okay, so stress is equal to E times strain. So now what happens is that we assume a structure which is bent like this. Okay, now we take this section A, B, C, D, okay, a small portion of this beam. So initially this section, these lines A, B and C, D, they were parallel to each other, and once you apply the load, what happens? The BD section, they move apart and the AC move closer, and that's what our moment is. That's what the moment does, doesn't it? So that's what has been shown over here. Now, in the case of if we have a structure which bends, yeah, what happens is that I told you that bending or having if a structure which was initially straight and it deflects, there is a term which is called radius of curvature or curvature that comes into play. How does that come into play? We need to quantify how much deflection, how much something has curved. Like, for example, obviously, if I've got this thing which is plane, okay, this is a plane structure. This is one type of curvature. This is one type of curve, isn't it? This is another one. This is another one. This is another one. So obviously, what happens is that my structure, yeah, there are different types of curves which are getting formed, and I need to quantify, I need to know, like, how are these curves, how can I distinguish one curve from another, which is like this curve from this curve? How can I distinguish it? So, how do I do that? I do it via radius of curvature. And where is the radius of curvature coming from? That is actually from something which is called curvature. Curvature. Okay? Now, for example, please, I need your concentration, okay? Over here. For example, I've got a curve like this. Okay? I've got a curve like this. How can I say that this curve and this curve, these two curves, they are different. They are curved differently. So we use something which is called curvature. And what is curvature? The curvature tells us that if we draw tangents at different locations, okay, how much is the rate of change of direction of the tangent? Okay, that is curvature. By how much rate this tangent, which I've called 1, is changing with respect to 2. So in other words, I've got this tangent. Yes, this is one tangent. This is another tangent. Okay? I work out the angle between these two tangents. Yes? So one is this tangent, another one is this tangent. So this tangent, one is this tangent and one is that tangent. Okay? And I work out angle between these two. Yes? That will give me one certain angle, which is, for example, one was this tangent and another one was the red tangent. This is the angle theta 1. Agreed? Yes. And similarly for this curve, I take the same point. Imagine this is the same length of string, okay, but having different curvature. I find out another tangent and another one, and this is theta 2. So that is something, this rotation between the two adjacent tangents, that is something which tells me how much this curve is changing. Like, for example, if you might have gone to Murray or in those areas. How do you know that when you are going on a steep uphill or less steeper uphill? How do you know that? It's based on slopes, isn't it? You are trying to find out slopes at different points. And if this slope is bigger between the two tangents, then that means it's a steeper one. And if it is less than this one, then that means it's a less steeper one, isn't it? So That's how, so that is actually your curvature. That's called curvature. So if you want to draw this curve, okay, you find out the tangent of these ones, of all these tangents, and find the difference between the tangents. Difference between tangents, tangent means theta, isn't it? Tangent theta is approximately equal to theta. So one theta you find another theta, find the difference, theta 2 minus theta 1, and you can draw this whole curve. And similarly, you can find out this curve and do the same exercise, and then compare these theta and find out like whether something is more curved or less curved. Yes, sir. Do you understand? So therefore we introduce something which is called curvature, and radius of curvature is the inverse of curvature. Okay, that is actually the inverse of curvature. Now you will see how that works. But imagine we have got the same deflected curve, which, okay, so this is I've taken a segment out of this one and I've shown it as a deflected section. Now I assume that if I draw a tangent at these 2 points, this is, I mean, in the middle we have E and F, okay? So EF, sorry. Okay, so do you agree that before applying any load, AC, EF and BD, they were all equal? Yes. Do you agree? Yes. Once you apply the load, what happens is that AC, I told you, comes closer, BD move apart, EF is at the center, and the center. So obviously, if there is something which is going in compression and there is something which was in tension, so there must be some layer where everything is zero, isn't it? Because this is extreme tension, then it becomes a bit lesser tension, then it becomes a bit lesser tension, lesser, until you reach a point where it's zero, and then the compression starts. So EF is that layer, which was neutral, which was, okay, so which didn't have any compression or tension. So at that layer, what we do is I draw a tangent. Okay, I draw, sir, please, I request, okay, please. So at this point, we draw a tangent, and similarly at this F point, I draw a tangent. Okay, then I draw a normal to this tangent. Okay, a normal to this tangent and a normal to this tangent. Do you understand? Yes, they will meet at one point. Why? Why would they meet at one point? Sorry, can anyone tell me why would they both meet at one point?
Because they are not parallel.
Because they are not parallel, because they are deflected, obviously. Geometry tells us they have to meet at one point. Because they are not, because this structure has deflected. Do you understand the relationship of mathematics, how it's coming to a rescue in structures and mechanics? Yes. Do you understand that? So they meet at one point, which is O. Okay, we call it O. And then from there we say, if these 2 points, they are very close to one another, then we can draw an imaginary circle which will touch E and which will touch F and all the points which are in between E and F, if these are very close to one another. Yes. Okay, let me ask you, if they are further apart, will this big circle touch all the points between these two? For example, if I take the end, if I take this end and I bend it, is it possible for me to draw a circle which will touch This is a simply supported beam which has deflected like this. Okay, a simply supported beam deflected like this. Can I draw a circle which will touch the two supports and all the points which are in the middle? Those who are saying yes, why? Huh? No, radius will be increased, but my point is for curvature. For radius of curvature, the important point is that a circle, you take two reference points, draw tangents, and then you draw a circle, and in between those 2 points, all the points which are coming in the middle, they should all be on the surface of the circle. So, do you mean that if I do this circle or this circle, if I keep on drawing, I will always draw a circle? Why no? Yes, because it is not a circle. This is a parabola, and parabola and circle is different. Why? Because in case of parabola, you have the radius of curvature that keeps on changing. The only curve whose radius of curvature doesn't change is circle. Circle has got radius of curvature equal everywhere, except that any curve you take, that has got radius of curvature changing as you move along. Okay? So therefore, it is not possible. That's why we say that we bring it very close to one another. Okay? Very close. So if these 2 points are close enough, then it's possible that you draw a curve and then you draw a circle. Okay? That circle is called circle of curvature, and that radius, the radius of that circle is radius of curvature. So, would I be wrong in saying that strain is change in length by original? Okay, now what happens is, before that, I've got AB like this, CD like this. You agree with me on that? Can I draw a parallel line like this, which is parallel to AB? This dotted line? Can I draw that?
Yes, sir.
Yes? Imagine I call it C1, C1, D1. C1 and D1. Can I draw C1, D1 which is parallel to this?
Yes, sir.
So this OD, is this a transversal which touches this point and this point?
Yes.
So can I say d theta and this d theta, they are same?
Yes, sir.
Do you all agree with me?
Yes, sir.
Yes. Okay. So imagine, so this one is rho. Okay. So I should say, call it rather. So now EF. What is EF? Can I write EF is rho d theta, S is equal to r theta?
Yes, sir.
Can I do that?
Yes.
So EF is rho d theta, and I want to find, I take one fiber somewhere, a random fiber, okay, somewhere at the top or bottom. I take it at the bottom, okay, and this fiber is GK. So GK initially was also, this is somewhere over here, okay, on this on the section which I am considering. So this GK was somewhere over here. This GK has expanded. Agreed?
Yes, sir.
Because it is below the neutral axis. If it was above, it would have been compressed. So it has expanded, and this GK, okay, this GK, by how much amount has it expanded?
HK.
This is HK. And if I consider this as Y, so my HK can be Y d theta if this fiber is at a distance Y from the neutral axis.
Yes.
So, can I write Y d theta
Yes, sir.
and rho d theta? Agreed? Anyone who is not understanding this? Because you know, this is something, this is the most basic, the first step to your structure mechanics. Okay, structure mechanics. This whole derivation is actually the stepping stone to your structure mechanics. Based on this edifice, based on this foundation, then you build your further additional mechanics. Okay, so this is very important. That's why this understanding of this whole process, how geometry is working with your forces and all that, is very important. Whatever we had done, we were dealing with forces, weren't we? We were dealing only with forces. Now what have we done? We have brought geometry also in it, because deflection is a geometrical issue. Do you understand my point? Do you understand why are we bringing geometry also in our equation? Yeah. So you have y by rho strain. Okay. Now this y by rho. Now we have summation of moments. Okay. Summation of moment about the y-axis must be equal to 0. That is our equilibrium equation, isn't it? So if I take this small patch or this small element, okay, and this element I assume is again at a distance y from the neutral axis. So my moment, okay, the applied moment must be equal to the resisting moment, isn't it?
Yes, sir.
So this is one. So this moment M is equal to stress x times dA. There is a stress x stretch which is in this direction, because as I told you that this is now stretched like this. So there is a stress which is stress x applied on this, isn't it? Agreed?
Yes.
So this is stress x times dA, which is force, times y. That gives me moment. So the applied moment must be equal to the resisting. The applied moment you get from where? From the bending moment diagram, isn't it? BMD tells you the applied moment.
Yes.
And internally, this fiber must be strong enough to take that, or all these fibers must be strong enough to take that load, isn't it? Do you agree with me?
Yes.
So that's what we are doing. Applied moment must be equal to stress x dA times y. Plug the values in this. What will we get? Stress x is equal to E times strain. E times strain y dA, and E times y square by rho dA, or E by rho y square dA. Now this quantity which is inside the bracket, this is called moment of inertia. Second moment of inertia. Yeah, this is called moment of inertia or second area of moment. Okay, this is your moment of inertia. It tells you how much stiff your structure is. Okay, if something has, in other words, I've got this paper. Okay, this paper can be easily bent. Yes, agreed? However, I've got this book. I've got this book. This book is very difficult to bend. I mean, by difficult, I mean relative to the force which I am applying. But initially, I mean, I didn't have to do any effort to bend the page. However, in case of book, I have to make some effort in order to bend it. So obviously, that is the property of your cross section. As the thickness increases, your stiffness, cross-sectional stiffness increases, and that's what this is the thickness, isn't it? Y square. So it is a function of y square. So as your y square, as you make this thing deeper, okay, as I keep on increasing this, this quantity, it becomes stiffer, and this thing increases. The stiffness increases. Are you getting what I'm saying?
Yes, sir.
Yeah. So this is called moment of inertia, and So this is your E I by rho, and that, okay, and that is equal to M. Okay, let me. So in other words, we can write 1 by rho is equal to M over EI. Are you all with me on this? If you don't understand, please stop me, okay? Now look at this. Why have I written it in this form?
Curvature is the inverse of the radius of curvature.
No, that's true. But what else can you see? What is on one side of the equation and what's on the other side of the equation? Geometry is on one side and force is on the other side. Yeah? That is what we have. Now how, let's see. Let's build our intuition. How the geometry is related to your moment. What is this telling you? If the radius of curvature is reduced, the moment is increased. How is that? How is that? I mean, like, does that mean, how can you make your common sense satisfied?
The beam will be more curved.
Yes, exactly. So what will happen is, like, look at this thing. Look at this. If I've got a bit flatter curve and I've got something like this, okay? If I draw tangent, this one and this one, this will meet somewhere at a very far distance. Okay? So that circle which I'll be drawing, that will be a very big circle. Yeah? So, but this is the bending, this is almost flatter. So this means that less moment has been applied, isn't it? Agree?
Yes, sir.
But in this case, if I do the same thing, this will just meet like this. Won't it? Do you agree with me? And my circle will be a very small circle. So but this has bent more. This has bent more. It's very steep. So that's what this equation is telling us. Do you understand that point? Yes?
Yes, sir.
Okay. Now we have developed this equation. Now let's develop an equation for deflection. Any issue with whatever we have discussed so far? Any issue? Please ask me. Yes? Shall we go further then? Okay. Now it's the same thing I have redrawn over here. We have the same segment. So now we assume that this is X and this is Y. The same thing, I mean, what we were doing over here. Okay? This is our neutral axis. Elastic curve is always with respect to neutral axis. You find out, so what happens is, what is this telling us? That you find out the deflection of the neutral axis. And then, once you know this curve, which is with respect to neutral axis, you can easily find out the stresses anywhere along this, because we have assumed plane section remain plane, isn't it? So this is a plane section and it has become like this. So I mean, you can find out stresses in every layer once you know the deflection and the stretch of this one, isn't it? Do you agree with me?
Yes.
So I mean that once you find out the deflection of the neutral axis, you can find out the deflection of this one. Why? Because you will keep on adding this y distance to it and you will keep on finding out your deflection of other layers. So that's why we take the neutral axis. Do you understand? Do you understand the logic behind taking the neutral axis? Okay, so now what happens is that I've got y and I've got x over here. I can write this is, imagine this is my theta. Okay, so I can write that this equation tangent theta is equal to dy by dx. The slope between any two points which are very close to one another, that is equal to dy by dx. Okay, and that tangent theta, because we have assumed that deflections are small, okay, they are very small, so therefore we can approximate this tangent theta to theta. Yes, so we have got theta is equal to dy by dx. Now I can differentiate this again. D theta by dx is equal to d2y by dx squared. Can I write that? Okay, now the same row, okay, this is our ds. This curve ds, so I can write ds is equal to rho d theta. Can I write that?
Yes.
And one by rho is equal to d theta by ds. Yes?
Yes.
Now, this ds, because we are taking small deflections, so this ds is approximately equal to dx in our case. It's not a string. Okay, a string can stretch, but we assume that deflection is a very stiff structure. So we assume that this ds is approximately equal to dx. Dx is this straight edge. Okay, so we assume that this ds is approximately equal to dx, and d theta we can write approximately equal to dx. Okay, is that okay? Do you understand the logic? Why am I changing? I mean, I'm not doing it randomly because my deflection is extremely small. Extremely small. It's not like this one which you can which you can visualize. Okay, it is extremely small. You can hardly differentiate between the between the undeflected structure and the deflected structure. It's so small. So I can say that this ds is approximately equal to dx. Agreed? Now, does this ring a bell? 1 by rho. What is this? This is m over ei. Can I write that?
Yes.
So we can write we make it as well as is equal to d2y by dx square. Okay? Now look, what is d2y by dx square?
Change of slope.
This is the change of slope, yes, what we are talking about. What is this slope is d theta by dx. And this one is also d theta by dx. This is the d by dx of dy by dx. And that is actually what I told you is what? This is equal to your curvature. And that is equal to 1 by rho. Remember, I started my discussion with curvature, and curvature is actually change of this slope. But there is some second order terms also which are in here, which we have included, which we have excluded, because the curvature, when you work out, there is something which is coming over here also. 1 plus something dy by dx, and this is 3 by 2. But that whole thing is ignored. You have done curvature, isn't it? You have derived curvature's equation, haven't you? In your mathematics, you haven't done? Okay, but anyway, there is the curvature formula. This is a simplified curvature formula. It has got a second order term also. Why? Because curvature can be for a string also. Because we are ignoring the large displacement stuff, we are just focusing on small displacement, that becomes 0. This dy by dx power 3 by 2 and that thing that becomes 0, and you are just left with 1. So when you derive the mathematical equation of this, you will get something like that. But you got the main understanding, I think so.
Yes.
Yes, that 1 by rho, that m over ei is equal to d2y by dx square. Okay? Now, let us write it down. This is the main deflection equation which we will be using. Okay? This is the main equation. Now, what will you be asked in your in the question? Okay? Or what will be what you will be required to find out in deflection? That is the equation, the parabolic equation of that curve. Okay? The parabolic equation of this curve you will be asked to derive. That's what would be expected from you. And how could you derive that? What do you think? How can you derive the parabolic equation based on this? Integrate. How many times? 2 times. So double integration. So the first method, which is the simplest method of deflection, is double integration method. You have done that?
Yes.
No, you have done it in your MOS 1. Yes. So in the the double integration method. The double integration method involves different integrating twice. Okay, you will come up with some constants, and those constants, how would you be working out those constants? Based on the boundary condition. Okay, so whether it's a fixed section structure, whether it's a pinch section, whatever it is, based on that you will work out your what you call your equation, the parabola, equation of parabola. Okay, shall I rub it off? Okay, so we will do now the double integration method quickly, just a refresher for you guys. And should I rub it off now? Yes. Okay, so if you get a structure like this, the first step is to find out your reactions. That is the first step. Okay? Once you find out your reaction, then then after that you will use different variety of techniques for finding deflections. Okay? The first method which we are going to do is double integration method. In double integration method, what happens is, sorry? No, in this case, I mean you will be given, if you check it, good enough. Okay? So I mean like, okay, apply, find out determinacy is just one liner, but after that you work out your reactions, and then after that you find out your deflections. Okay, so this is, so once you do structure analysis, you will get 480 Newton, 920 Newton, okay, on these two supports. Now, as we discussed, M over EI is equal to d2y by dx square. That's the main equation. Okay, this is the main equation of your double integration method. So you have to find out what? Moment. Normally, either you will be given EI or you will work it out in terms of your EI. Okay, because these are constant. So d2y by dx square is equal to m. That is the main equation which you have to focus on. Now, how do you find out m? That is a bending moment diagram. In this case, we have A, B, C, D. How would you find out your bending moment diagram? I mean, there is a problem specifically in this equation, in this structure. Not problem, I mean like, what is, this is m over EI is equal to d2y by dx square. And we normally want one moment equation. If we have one moment equation, then that makes our life easier rather than having multiple moment equation and applying it. Because if we have to apply it on multiple moment equation, then between them we have to find out some constant, we have to join it, isn't it? If you mathematically, if you divide this being, okay, let's do it, let's organize our thought. In this, first point is that we should have one moment equation. Okay? And one moment equation, that is easy. Why? Because you can then easily apply this condition and you can find out straight away your deflected curve. What happens in this problem? In this problem, can you have one moment equation?
No, sir. No, sir.
You will have for AB, no, it's not matter of linear or non-linear. It is for AB.
One equation.
And AB is equal to 480 times X. Okay? Agree? For MBC, you will have X coming here, so you will have
480x
80 times x minus
500 into x minus 2.
and for NCD we will have again x. Look, I would have 480 times x minus 500 x minus 2 minus 450 into x minus 3
x minus 4 center.
Okay, what am I doing? What's the issue? When you draw your shear force and bending moment from the first principle, what do? If someone asks you to find out moment at this point, what do? You find out it. You find it out in terms of x, isn't it? X is a limit. X is in this direction. Okay. So for AB, you will have a separate equation like this. For BC, your x will come in here. Okay. So 480 times x minus 500 x minus 2, and for CD, x will now come over here. So you will have 480 times x, 500 x minus 2, and 450 times x minus 3. What do you mean minus 4? X minus 3 is 450 times this, and then x minus 3 by 2. What is x minus? What do you mean x minus 4? This is a general. X you don't know. It is where the x is. X should work between CD. So now, if I want to use CD, this equation, then what will happen? I just want to use this equation. Can I use this equation for this section?
No, sir.
Why?
Because there is a limitation on x directly from range.
What will happen? Okay, if I use it for this one, what will happen to this? What will be this?
Negative.
This will be negative, which is wrong. And this will be negative again. Because x is less than 2. So for this, in order to overcome this, what we use is something called Maclaurin brackets. Okay? And what is that? I've rewritten everything, but I've put these brackets. And these brackets, they won't accept negatives. They will kill it to 0. Okay? So they will kill that term if it is negative. So in other words, if my x is for this region, so this term will become 0. This term will become 0. And I would have only this term. Now, if my x is over here, what will happen? This term will exist. This term will exist because it's bigger than 2. This term will become 0. And if its x is CD, then all of 3 are active. Okay? So that's what we use. We use these pointed brackets and we develop one equation. Okay? And then we can solve easily this one. So do you understand this thing? Now, I will solve one problem for you and then I'll give you some assignments, okay? So the rest in assignment. Because this is a strict G. Yes. Why? You haven't written it. I'll rewrite it.
No, sir.
said it's okay.
Huh?
He will copy mine.
Okay. Should I wrap it off?
Yes, yes, sir.
This is a very straightforward question. So the first step for you guys, okay, so you check the second step is analysis, which is this is summation of moment at c is equal to 0. Okay? Please check. Since this load is closer to C, that's why C will take more load and A will take less load. Okay, so please do this sort of sense check. Okay, yeah, whether it makes sense or not. Another thing is like these two must add up to your applied load. That's another thing. Okay, so that's the structure. Now double integration method. Okay, so what should we do? First of all, we'll write the moment equation, isn't it? So moment m is equal to, we have got two sections, so again we can take this one. Yeah, m is equal to, you just take x till here, so this will be Okay? Now, agreed? This, no, this is x is here. Okay, we are taking moment about this point. Okay, so that is x minus 2, isn't it? 300 into x minus 2. How can it be x minus 1? So in another step, we can write something like this, and that is equal to 100x this is just a fancy bracket. You will do whatever you do normally. You do normally in integration. Okay. The only thing is, the only additional condition is that this will become 0 if it is negative. That's all. Okay. The rest you treat it just like it's a simple curved bracket. That's it. So integrate first. EI dy by dx is equal to 100x squared by 2 minus 300 plus C1. Then EI y is equal to
x cubed by 6 by 6x cubed. X equals to 1 cube.
okay. Okay, now what should we do? How can we find out RC1? So this is our equation A and B. So no, this is A. This is the same one. This is our equation A. And this is B. Okay. So how can we find out C1? What is the boundary conditions? No, this is, what is this now?
From 0 to
What is the boundary condition for this one? At x is equal to 0, use boundary conditions. Okay, so what do we have? we have at x is equal to 0. Isn't it? Because this is a simply supported beam, so the rotation over here is 0 and deflection. So this is correct?
Yes.
Is everyone agreeing with me that this is correct?
Why? So why is it what?
Why is this correct? This is not a fixed support. This is so. This is not correct. Deflection is 0, but rotation is not 0 because the elastic curve is something like this, isn't it? So there will be some finite rotation. So at x is equal to 0, y is 0, and at x is equal to 3, y is equal to 0. These are the two conditions. Agreed?
Yes.
So now you put these put in B. So at x is equal to 0, y is equal to 0. So C2 comes out to be, what is C2? C2 is equal to 0, isn't it?
Yes, sir.
At x is equal to 0, this one becomes negative 0. This one is 0. This one is 0. So, and y is 0. So your C2 is 0. And at x is equal to 3, V is 0 is equal to how much is C2? No, C1. Huh? Sorry. This is
minus 133.33.
C1 is equal to
Minus 133.3.
Okay? This is the deflected curve. If you are asked to find out the maximum deflection, so how would you do that? No, you have to find out where the maximum deflection is. Huh? No. You have to find out is it true?
Yes.
At maximum deflection, slope is 0. So you differentiate this one. So if I differentiate this, what will happen? Ei dy by dx is equal to
100x square by 2. ऊपर लिखी हुई है देखो ये.
So this is the same equation, which is this one, isn't it?
Yes, sir.
So you just put the values in this one. So make this equal to 0.
Yes, and multiply it.
And C1 is minus 133, and you find out what the x is. How can you find that out?
Quadratic equation is
This is quadratic equation.
yes.
So can your calculator solve this?
Yes, sir.
It can, yeah. So you can just use numerical method to solve this equation or whatever, but you will get use your calculator. If it does it, use your calculator. Okay, no need to do the quadratic equation from first principle. Just use your calculator and find out your x. Where
There will be two answers for x.
so in the case of two answers, what can happen? Okay, can anyone solve it quickly? Do you have a calculator to solve it? We will take the attendance and please someone solve it, and I'll show you what. What do you get? What's the solution? Why is it taking so long?
0.91.
Huh? 1.7. You would have two answers.
Yes,
One would be
0.91.
one would be within the span, one would be outside. How much?
1.7 and 4.2.
Okay. Can anyone second it? X is 1 point
7.1.
and 4 point.
1.2.
Sir, 5.56 and minus is 0.76.
No, that's wrong.
So C1 down.
Anyone else? 0.91 and
5.08.
I think there's some mistake in C1.
this sound 0.91, I don't know. Has anyone else got this one? Can you double check?
Yes, sir. 1.71 and 4.29.
Yeah, this one is correct. So 4.29 is not possible, so 1.7. Okay, can someone come please and take the attendance? Okay. Anyone, come on, hurry. So you can put this value back in this equation and you will get y. Remember, you will get your y in negative, which means like according to our sign convention, was negative.
Hafaz Hamza, Ahmad Yasin, Ahmad Faraz, Hasan Habib, Anwar ul Haq, Awais Bashir, Chaudhry Mohammad Salam,